Hello everyone, my name is Protik Acharjay and today I'm going to talk about irregular sequence counter. So, at first we have to know what is counter. The devices are used for counting is called counter. Counter is made of flip-flop and these are basically sequential circuits. There are two kinds of counter one is asynchronous counter and another one is synchronous counter. Irregular sequence counter is one kind of synchronous counter. In this presentation, I will implement an irregular sequence counter by given sequence which is 5, 1, 3, 7, 2. Irregular sequence counter has many real-life examples like alarm clock, set timer, and flashing light indicator, etc., which we use in our day-to-day life. There are 5 steps in to design an irregular sequence counter. Those 5 steps will describe in my further slides, but at first we have to develop a state diagram, then we have to develop a next state table, then create a flip-flop transition table, and then we have to use KMap for deriving the logical requirements that for implementing the counter. Then at last we can implement the counter. So let's jump into the first step, which is developing a state diagram. So by the sequence we can see 5, 1, 3, 7, 2. In those the highest number is 7 and its binary is 1, 1, 1. So if for my counter is required only 3 flip-flops. So this is how a state diagram looks. Next we have to develop a next state table where we have to represent present state and next state. As we see before, the sequence 5 after 1. So in this case 101, which represent the 5, and then the next state will be 1. So 001 is represents 1. So then we have to go for step 3, which is flip-flop transition table. It is very much important for go through the next step, and we have to define the j k values very carefully, because in this stage if we have any kind of problem, then it will cause uh, very much problem further. So after this we have to use KMap for deriving the logical requirements. So in this KMaps we have to solve it, and the logics are J0 is equal to 1, J1 is equal to Q2 bar, J2 is equal to Q1, and then we have K0 is equal to Q2 and Q1, K1 is equal to Q0 bar, and K2 is equal to 1. So this logics will implement in the counter. So by the multisim software, this is how after implementing the counter it looks. So we will see the how it will run and the simulations of the counter. So as you can see, our sequence is maintaining here 5, 1, 3, 7, 2, again 5, 1, 3, 7, 2. So like this, in the conclusion I can say that the every step is related to another step. So it is very important to focus and completely into those tasks, otherwise it will be a great wrong result at the end. So I have done all the steps very carefully and successfully. I am able to show all the counting by the multisim software. So These are my reference. Most important is the class and slides, which helped me a lot, and for further research and some confusions, Google and YouTube helped me a lot. So thank you, sir, and thank you everyone whoever watched this presentation so far. If you guys have any kind of question, then please feel free to ask me. Thank you.